Welcome back. In part 1, we saw it was pretty easy to calculate the number of pulses needed, the step resolution, and the motor speed. In this video, we'll learn how to calculate the torque required and then use that and the motor speed to select a motor. We'll also take a look at how to use all that information to do the exact same thing for other types of mechanisms. Here we go. Step 4. How much torque do we need to move a carriage on a linear slide? The total torque we need to worry about is how much torque it takes to keep things moving and how much torque it takes to accelerate the load. And acceleration torque is just the inertia times the change in speed over the change in time. What exactly is inertia? Well, it's just a measure of how much an object resists being moved, and it's solely dependent on the mass of the object. For example, which is harder to get moving, a clay brick or a styrofoam brick? Well, the clay brick, of course. Why? Because it has more mass. And because it has more mass, it takes more force to get it moving. That force has to be large enough to overcome what? The inertia of the object. So inertia is just a measure of how much an object doesn't want to be moved. And since we're rotating stuff here, we need torque to get it moving. Get what moving? Well, for the linear slide, the motor has to rotate, the gearbox has to rotate, a coupler has to rotate, the screw has to rotate, and the carriage has to move. And all of those things have mass, so they all have inertia, which means they're all going to work against us when we try to get things moving. So we need to sum all of those inertias to get the total inertia. And the gearbox impacts the inertia of everything behind it by the square of the gear ratio. In our example, we don't have a gearbox, so there is no inertia, which means the gear ratio is 1 to 1, so that gets rid of this term. If you look in the SureStep user manual, Appendix C, there's a whole bunch of scary-looking equations that show you how to calculate all of this stuff. And while you can do all that math if you want to, there's a much easier way to do it. For the motor inertia, we just go to the spec sheet and see the inertia of the rotor is 0.56 ounce-inches squared. If you don't know what motor you're using yet, just leave it blank. You can add it in later once you've selected one to make sure it doesn't affect anything. And if we go to the lead screw spec sheet, look at this. It's already calculated the inertia of everything associated with the linear slide. And it gives us a factor we multiply the payload mass by to give us that inertia. Now be careful here. Is this the weight in pounds? No, it's mass. And since force is mass times acceleration, we just divide the payload weight by the acceleration, which is gravity in this case, 32.2 feet per second, or since we need inches in this example, that would be 386.4 inches per second. This slide can handle 110 pounds, so let's divide that by the acceleration to get our mass number, multiply that by the handy inertia factor, and now we have the inertia for this payload and the system inertia of the carriage and coupler. Let's add those to our chart. If we had a gearbox, same thing. Just get the inertia from that data sheet. We don't have a gearbox, but if we did, we would put its inertia here and divide the downstream inertias by the square of the gear ratio. Now this is really important. We need for all of our inertia values to be in the same units. For this demo, we want ounce-inch-second squared. So when we're done, we can just read the answer right off the motor curves, which are in ounce-inches of torque. The only problem is all these units are different. And how in the world do you convert these units with inches squared to these units with seconds squared? That doesn't seem right, does it? Here's the trick. Go out on the web and search for an inertia units converter. Put the units you have here, the units you'll want here, and there's the answer. Easy. Here's all of our inertias converted to the correct units. The bottom line is, we didn't have to do any math, did we? Automation Direct provides all the inertias we need in the data sheets, and we used an online calculator to do the units conversions. To get the acceleration torque, we just sum those, multiply by the change in speed in revolutions per second, which we found back in step 1 of this video series, and divide that by the change in speed in seconds, which is our ramp time. To get rid of this revolutions term, we just multiply by 2 pi radians per revolution. We now know the torque we need to overcome the acceleration inertia. The other torque term is just the torque needed to overcome friction and gravity and any other external influences. Gravity is important if you're lifting something. We aren't, so we'll set that to 0. Friction is if there's any additional drag on the system. That was built into the numbers we got from the data sheet, so we can set that to 0. The external torque is to account for any other additional drag that might be placed on the system. Maybe you're pulling something out from a stack and the weight of the stuff above it is adding to the drag, for example. We don't have any of that, so we'll set that one to 0. So we just looked up the inertia numbers in the data sheets, summed them, multiplied them by the change in speed, and divided by the change in time. That's it. We now have the torque required by the motor and the max speed, so we can flip over to the motor curves and see how we stack up. Our max levels are 720 RPM and 1.7 ounce-inches of torque. As you can see, we're not even coming close to stressing this motor, even with the full 110 pounds of load on the slide. And that's not really a surprise because all of the weight's being supported by the slide, not the motor, and a 0.2-inch screw has a lot of mechanical advantage, which also explains why we didn't need a gearbox for this application. Now, for applications where more torque is required, we recommend that you leave yourself 50% headroom on these charts. Treat these curves as the absolute maximum that you do not want to exceed. Now, what if you wanted to use belts and pulleys instead of a lead screw? Well, it's the same thing, right? You just gather up the inertias, calculate the torque, and look up which motor you need to do the job. The only difference is you're not going to find a lot of the inertia values for pulleys and indexing tables, so you will have to fall back to the equations in the user manual to calculate those. The good news is there are step-by-step examples in the user manual showing you exactly how to do it for all three: linear slides, belts and pulleys, and indexing tables. Which reminds me, did you know that Automation Direct has a free tool that helps you with all of this? It's intended for servo systems, but it works perfectly for steppers too. You just build your system, enter each device's specs, specify your velocity profile, specify your motor, and you instantly see how much torque you'll need. And it even handles S-curves and triangular and trapezoidal profiles. You can then view your system performance. Here's what the motor is capable of peak and rated, and what your system requires, peak and RMS. If you do a lot of this kind of stuff, it's worth spending the time to learn how to use this really cool tool. Regardless of how you calculate the inertia, please remember that these calculated numbers are just a good starting point. You still need to apply some experience and common sense. So how close are these numbers that we just calculated to the actual measured numbers? Well, check out the next video where we compare these calculated numbers with real live results. If you need any help with selecting an Automation Direct stepper motor, please contact Automation Direct's free, award-winning support team during regular business hours. They'll be happy to help. And don't forget the forums. There are lots of folks there that love to share their years of experience. Just don't post any questions directed at Automation Direct support staff there. They don't monitor the forums on a regular basis.